Hey everyone, welcome to The Explainer. Today we're diving straight into something absolutely crucial for making machines genuinely intelligent. We hear about AI literally everywhere right now, but the real secret sauce? Well, it's not actually just the algorithms. It's really all about how we engineer and filter the massive amounts of information we feed into them. It's about finding that signal through the noise. So let's get right into it.
Okay, so think about this for a second. How does your brain instantly know the difference between, say, a walnut, a cashew, and an almond? You aren't just staring at a random pile of food, your brain is rapidly sorting them out based on very specific characteristics, things like color, size, texture, and weight. In the machine learning world, we call these characteristics features. And just like you unconsciously train your brain to recognize these features to make a smart decision, we have to do the exact same thing for computers if we want them to be intelligent.
So here's a quick look at our agenda for today. 1. Welcome to the AI landscape. 2. How machines actually learn. 3. The overfitting problem. 4. The curse of dimensionality. And 5. Extraction versus selection. Let's start with section 1. Welcome to the AI landscape, the macro view. Now, if you want to understand all these buzzwords flying around the tech world today, it really helps to think of them like Russian nesting dolls. Artificial intelligence is that biggest doll on the outside. It's the broadest concept of programs having their own decision-making capabilities to basically mimic human behavior. Pop that open, and inside you find machine learning, the orange doll, which uses some pretty complex statistical techniques so machines actually improve with experience. Open that one up, and you get deep learning, the smallest green doll, which exposes these multi-layered neural networks to just vast amounts of data. But why does this all matter so much, especially for us in applied fields like mechanical engineering or business? Well, the stakes are literally massive. A whopping 80% of executives report that AI drastically boosts productivity, and it's even creating entirely new positions. We're talking about everything from predictive maintenance to automated process control and defect detection. Optimizing these systems, it's not just some fun lab experiment anymore. It's absolutely the future of modern industry.
Moving on to section 2, how machines actually learn, the ML pipeline.
So here we have the classic 5-step machine learning process, and it always starts with step 1, getting the data, or data acquisition. In mechanical engineering, this usually means taking real-world physical systems, picture a spinning turbine or a running engine, and using sensors and transducers to measure things like temperature or vibration. Then, we digitize those analog signals into ones and zeros so a computer can actually understand and analyze them. From there, we move through cleaning the data, training our model, testing it out, and finally improving it. But the absolute make or break moment, it's right here in step 2, cleaning and preparing that data. Remember our mixed nuts from earlier? If we just dump all that raw data into a computer, it's going to get totally confused. We really have to isolate the vital variables, the features, so the model can actually learn the underlying patterns instead of just blindly memorizing a giant mess of raw, unfiltered information. That brings us to section 3, the overfitting problem when learning fails. Because think about it, what actually happens if we skip that filtering step and just feed the machine absolutely every single piece of data we have? Well, that leads us straight into overfitting. Overfitting is basically what happens when a model trains on redundant data and a bunch of unwanted noise. At first glance, it looks like it's performing amazingly well on the training data, but then its performance absolutely tanks when you test it on new, unseen data. In short, cramming in too many useless, complex variables totally destroys a model's ability to generalize to the real world. Actually, a great way to visualize this is by looking at 3 students taking a class. Student A is our underfit model. They just don't care, they guess on everything, and they failed the test with a 47%. Then you have student B, our overfitted model. They are totally Mr. Know-It-All. They literally memorize the textbook word for word and ace that last quizzes at 98%. But because they just memorized data and didn't really learn the core concepts, they completely bombed the final exam with a 69%. Finally, student C represents our ideal best fit. They actually learn the underlying concepts and how to solve problems, scoring a solid 89% on that final unseen exam. Obviously, we want our AI to be student C. Now, look at the mathematical equivalent of our over-prepared student B. Instead of finding a nice, smooth trend line that understands the general direction of the data, the overfitted model is this chaotic, wavy green line. It is literally bending over backward to perfectly hit every single red training dot. And the problem is, that includes all the random noise and errors. So when new data points drop in later, this wild line is going to completely miss them. which leads right into Section 4, the curse of dimensionality, the pain of too much data. Let's do a quick thought experiment. Imagine dropping a coin on a straight 100-meter line. How do you find it? Super easy, right? You just walk the line and look down. That's one dimension. Now imagine finding that exact same coin somewhere on a 100 by 100-meter football field. Definitely harder. Okay, now imagine a 100 by 100 by 100-meter space. Your football field now has a 30-story height. Good luck finding a single coin in all of that. This exact phenomenon is what data scientists call the curse of dimensionality. Because as you add more dimensions, which in machine learning just means adding more features or variables, the density of your data completely plummets. You can see this peak and sudden drop on the performance curve here. Your classifier's performance improves at first, sure, but once you cross that dotted line representing the optimal number of features, adding more features actually makes performance drop. To maintain your accuracy in that giant 30-story stadium, your amount of training data would have to grow exponentially fast. And honestly, most of the time, we just don't have that much data sitting around. And that brings us to Section 5, extraction versus selection, the micro solution. So how do we solve this curse of dimensionality? We use feature engineering, which generally breaks down into two main approaches, extraction and selection. Feature extraction fundamentally transforms and compresses your big data set. It removes the redundant features by creating entirely new, combined features from the existing ones. On the flip side, feature selection doesn't create anything new at all. It simply acts like a filter, tossing out the redundant features while keeping an optimal subset of your original features exactly as they are. Let's look at a really popular method for feature extraction called Principal Component Analysis, or PCA for short. Imagine your raw dataset is this chaotic, noisy stage packed with overlapping instruments. We're talking multiple drum sets, 5 guitars, 3 violins. PCA acts like a master conductor. It extracts the essential information and cuts through the noise, mathematically concluding that, hey, you really only need one of each instrument type to get a great performance. And how does it actually pull this off? Through a pretty rigorous statistical process. You record the data, subtract the mean to center it, and determine a covariance matrix to see exactly how all these variables relate to each other. Then you calculate eigenvalues and eigenvectors, which honestly is just a fancy mathematical way of finding the directions of maximum variation in your data. The end result? You transform a massive set of highly correlated, redundant variables into a much smaller, uncorrelated set of new variables called principal components. And the best part is, they still retain the vast majority of your original information. Now, conversely, if we're doing feature selection, we might use filter methods based on an intrinsic property called entropy. In this context, entropy is just a mathematical measure of the impurity, uncertainty, or general disorder in your dataset. By measuring entropy, algorithms can calculate the information gain of a specific feature. Simply put, it measures the reduction in uncertainty if we keep that specific feature around. If keeping a variable doesn't provide enough information gain, the algorithm just says nope and drops it. And this brings us right back to the absolute golden rule of machine learning. And honestly, the whole reason everything we've talked about today matters. Garbage in leads to garbage out. If you feed a machine learning model irrelevant, redundant, and noisy data, it literally doesn't matter how sophisticated your deep learning neural networks are, you're going to get useless predictions. Feature engineering, smartly extracting and selecting the right data, is what enables algorithms to train faster, boosts their accuracy, and makes the model actually work in the real world. So, as we wrap up this explainer, I want to leave you with something to really think about the next time you're staring down a massive dataset in your engineering projects. If your machine learning dataset was an orchestra, are you feeding your model the actual music, or are you just overwhelming it with the noise? Thanks for hanging out and learning with us today. Keep asking those big questions, keep engineering those features, and we'll catch you in the next explainer.